Okay, so basically what they're going to do in section 1.4 and a little bit in 1.52 is kind of talk about this. They don't really talk about it, but it's like a family of functions, okay? So there's all these different types of functions that exist out there, polynomial functions, rational functions, trigonometric functions, all kinds of different functions that are there. So they're kind of just introduce you to polynomial functions, and then they start off in this one with some root functions, right? So like a square root or a cube root. Like this, or like this. All right? And if we graph a square root, it's going to look like that. And if we graph a cube root, it's going to look like this. And if we were to continue on with all the different root functions, you'd see that the even ones are going to look like this, and the odd ones are going to look like this. Because if you take an odd root of a negative number, you can do that, right? You can't take the square root of a negative. Okay? But an odd power or an odd root you can, because -1, the cube root of -1 is just -1. So that's why it shows up down there in the bottom. You can check it out if you want to and see that that's what you're going to get. All right. So those are square roots or roots or anything like that. They talk about those a little bit. So like the domain of this, what would the domain of that one be, the square root?
X cannot equal 0.
Oh, we can take the square root of 0, okay? What can we take the square root of? So then what does it mean the domain's got to be? There you go. Greater than or equal to 0, okay? All right. What about the range? Same thing, I heard somebody say, yep, got to be greater than or equal to 0, okay? Not only can't we take the square root of a negative number, we're not going to get a negative number for an answer. All right, so it's got to be greater than or equal to 0. On the other hand, this one, what's the domain of a cubic root? All real. And the range? All real. Okay, cool. So they talk about that. I see that they mention the word, they say this function is increasing, which it is, because it's just going up, right? Like this. So it's just going to continue, so it just keeps going. Not very much, but a little bit. So we say that would be increasing from 0 to infinity. And this one doesn't have that bump in there like that, but it's it's just kind of going like this. So it's just slightly increasing and then it keeps going, right? Okay, from left to right. So this one's just increasing. From negative infinity to infinity. All right. Does that kind of make sense? Yeah? Okay. And then they talk about maxima and minima. Okay. So here, that's our minimum. All right. The other one doesn't have any minimum or maximums because it just keeps growing. And the square root doesn't have any maximum because it keeps growing. All right. That's pretty much it with those. All right, so those are square roots or cube roots or any other roots you can think of. They're all going to be that. Evens are going to be here. I guess I can say this. This is going to be an even root, and this is going to be an odd one. They're all going to look like that. They're just going to oscillate back and forth. Okay? Then they talk about this one. And that's an absolute value. And I think we talked about this a little bit last week. I asked you if what that was. You said, well, that's absolute value. All right? So it looks like this. What's the domain of this? Yep. What's the range? Yep, greater or equal to 0. Okay. And it has a minimum, right? Right there. Increasing. So we could say increasing from 0 to infinity and decreasing from negative infinity to 0. Actually, I think I'll put a parenthesis around those. There we go. Going down and then going up. All right, so we call that decreasing and increasing. That's absolute value. Then they just keep going here. They do these. And I'm just gonna generalize a little bit more. So these are called power functions. So anytime you have x to a power, that's called a power function. So what do you think this graph is going to look like if n is an even number? What letter of the alphabet would you use to describe it? Yep. It's going to be a U. Okay? For odd, it's going to look like that. Can't get a letter for that one. Okay? And these are called power functions. And even the square root and the cube root are power functions technically. All right? Those are all power functions too.
So we can tell the difference between the odd and the even and the end of the graph?
Say that again.
Can we tell the difference between the odd and the even in the graph? Is that?
You could, the difference as far as, you mean like if you were just given a graph, would you?
Like the end, it says here n is even, and then the graph shape of you, and then the odd end is like, so this is how we can tell the difference?
That's how you would tell the difference if you were just given a graph.
Okay.
Right? But you wouldn't know whether it was a 4, 6, or if it's a U. We don't know if that's a 4 or 6 or an 8 on the power, right? But you know it's not odd. Okay. If it's a U shape, you're going to get an even number.
So if if it's a power of, and that power is an even number, the graph is going to be even symmetric to y, right? And then if it's odd, then it will be symmetric to the origin.
Yeah, and I mean, we could spend some time and I could show you with some sliders and decimals how that's going to work. But I think you probably pretty much know if it's you're going to get a U shape if it's even, and otherwise you're going to get a, you know, that little, I don't know what you want to call that, something. That's what you're going to get when it's odd. Okay. Like I said, you can easily explore that. But I'd rather explore other things that you haven't seen before, I think. So those are powers. They also have one other one here, and then, oh, well, we're good. This one. And in the book, they call this a reciprocal function. But it's really just a rational. It's just a really simple rational function. Okay? And it's going to look like this. That's what that looks like. And they're usually going to have some type of bending. I call this like a bending up here and a bending down this way. This is just getting really, really close to that x-axis, but never touches it. Because no matter what we put in for x, 1 over, could we ever get 0? 1 over a million's close, right? But not quite. And 1 over a billion and 1 over a trillion and so forth. It's close to 0, but never ever really gets there. All right? And the same thing happens here. All right? It gets really, really close to 0, but never gets there because we can't put 0 in it. Right? Okay. So in this case, this domain, what would the domain of this be? X. Well, it could be less than 0, right? Because we got all this stuff back here. Can't be equal to it, though. Right? And the range? The same. So that's the domain of those and the range of those, and that's a rational. Again, that's also considered a power function. It's just the power happens to be a negative number. All right, so most of these are power functions except for that absolute value one, which is not. So those are the ones that they bring up in here up until this very last one, which we'll take a look at before we break here. All right, so they talk about the roots, the absolute value, the reciprocal they call it, but it's really just a rational. And they bring up absolute value again, not sure why. All right, but they do. And then there's one more. So let's go try this out. I'm going to have to switch to here. Okay, so go ahead and get into Desmos if you're not already. And I want you to try some graphs out. And let's chat about them before we take a break. Okay, so here we go. So we're going to go y equals. And I want you to go to functions, which is right here. If you're using your phone, it's nice, probably abbreviated FUNC. All right. And then we're going to go to miscellaneous right here. And we're going to pick ceiling. Looks like seal right there. And then put an X in there. Now, what does seal do? Actually, it does not. But that's a good thought, though. I like that. I like your thinking that. What does it do to the number? Like, what if we wrote down the seal of 3 or the seal of 3.5? What's it do to 3.5? Let's go find that. Is this 3.5? No, that's 2. Here's 3.5. What's it do to it?
Taking out all the whole numbers. You just stick with the whole number on the y-axis.
You're really close. So if I put 3.5 right there, and I'm going to make sure I understand kind of what you're saying. So if we look at the whole number of x, that would be 3, right? Okay, but it's really, what does it take, instead of it being 3, what is it really? What is this giving us? So the y-coordinate is what? 4. So even if I go to 3.9, what's the y-coordinate? And 3.1. So what is it doing to the number? You're right, it's making it whole. But it's not just chopping it, right? 3.4, 3.1, 3. All those. It's getting rid of the decimal, and it's doing what to the number? By, I'm looking for a special word here. Rounding. Which way is it rounding? Which way is this rounding? It's rounding up. Okay, so this is rounding up. All right, so when you were thinking there was going to be asymptotes in here, look what happens right at 2. Okay, and it's really hard to see that. There's 2, 2, but if I go up here, see where 2, 2 is on the bottom? But as soon as I just budge it, it jumps up there, right? So 2.000001 is going to round up to 3, okay? So 2 is going to stay where it is, but 2.01, there's 2, and then 2.01 is going to pop up there, okay? So that rounds up. Now what was the name of this function? Oh, and it rounds up. Ceiling, right? Up. Ceiling's up. Okay? It's going to round up. All right? Try this one out. Y equals functions, miscellaneous, floor. What does floor do? Rounds down now, huh? See? 1. So this is kind of what you were talking about before, where you were saying it chops off, kind of gives you the whole number. Yeah. As soon as it hits 2, it jumps up. See how it jumps up at 2? But anything close to 2, just going to chop that right off and make it 1. All right? And this is floor, because where's the floor? down. Seal rounds up, 4 rounds down. Last one. Y equals functions, round. Now what do you think this is going to do? It's going to round down to the center. I think you're right. So we call this one rounding to the nearest. This is how everybody rounds. Well, not everybody, but some things are rounded up and down. Okay? It depends on what it is. By the way, income taxes are done this way. They're on a scale, and they're on some sort of a step function. Okay? And some of your mailing rates, parking, are all done this kind of way. Okay? Rounding is rounding to the nearest. So if I have 2.6, that's going to round to 3, right? 2.5 is going to round to 3. But as soon as I bump it to 2.4, that's going to round down to 2. Because 2.4 is closer to 2 than it is to 3. It's your usual round. Right? So normally if it's 2.5, you round up, right? That's all it is. It's just your typical round. Okay? So these are kind of interesting functions that are out there. All right? And when you come back in about 5 minutes or so, we'll do some more. All right? So there you go. You can take a little break if you want. Come back in about 5 minutes, and we'll do some more. Let me do this. We'll zoom this a little bit. All right, so let's review a little bit about what we just did with those functions. Okay, what did seal do? Rounds up. Okay, and then we had floor. What did floor do? Good. And then the last one was round, which rounded? Nearest. Okay, those are in Desmos, all right, as your as those functions are, all right. So, however, in mathematics we have what is called the greatest integer function. And it's symbolized in a couple ways. One looks like this. Okay, I've also seen it written like this. All right, both ways. This book uses the INT. And this is very, very similar to floor. So if we tell it to take the greatest integer of 1.4, it's going to round that down to 1. Okay? And if we tell it to take the integer of 1.9, it's going to round that down to 1. But if we tell it to take the integer of 2, then it's going to round that up to 2. All right? That's called the greatest integer function. It's also in the textbook there. And it looks like this. 4, 1, 2, 3, -1, -2, 1, -2, -3. We'll put in this hot pink. So anything from 0 to here with an open dot. I'm trying to draw that with an open dot there. Bless you. With an open dot is on there, so 0.5, 0.8, 0.9. As soon as it hits 1, it pops up to here. Then we have another open dot, pops up to here. Then we have another open dot, pops up to here. And then we have another open dot. All right? And it works with negatives too. It's the same thing. Open dot, open dot, open dot. Okay? That's the greatest integer. That's what that looks like. So it's pretty darn, it's pretty much floor. That's basically what it is. What's the domain? All real numbers. What's the range? Close? What kind of numbers are in the range? 1, 2, 3. What else we got? Man, you're getting closer. Right? 1, 2, 3, right? And then what about negatives? What negatives do we have? Negative 1, 2, 3. What are those? Integers. There you go. Okay, all integers. Right? Good. Okay. They also do just a little tiny little blurb in there about a discontinuous function. Discontinuous. There's just a tiny little bit on it. It's probably worth mentioning. Here's basically what it is, okay? A discontinuous function, a function whose graph, when traced by a pencil, pen, put in whatever you want, okay, must be lifted to complete the graph. That's not a mathematical definition by any means, but it's basically what happens here. So if I take, and I'm graphing like this, and now I go like this, and all of a sudden I have to lift up the pencil, okay? So I have to now come over here and lift this up. Okay, like that rational one we drew, that's discontinuous because I got to lift it up to finish it. So it could look like that, or it could look like this. Oop! I got to jump over that hole. Okay?
So it's like a not equal to?
It's just a graph that you just have to trace it. You just got to physically lift up your pen or pencil to complete it. Okay? That's a discontinuous graph. A continuous graph is pretty much everything that you've done, right? All those parabolas and lines and things you drew before. I mean, even most of the ones we've done tonight have been all continuous, right? Yeah. Okay. Any questions on the greatest integer or the discontinuous? Okay, one last one. Okay. Piecewise function. All right. So a piecewise function is a function that's defined in pieces, basically. So in this case, we have this piece here, which is a line coming down. We have a parabola here. And then we have another piece of a line going that way. All right? So this is a piecewise function because it's defined in pieces. I'll show you what one looks like. Has a big old curly cube function. And let's see, it'll say this. So it'll look like that. Or something pretty dang similar. Right here? That's all right. Let me clean it up a little bit maybe. Is that better? Okay. So, this has two pieces, and it has what we call two conditions. All right? This part and this part are the conditions. All right? So, let's look at this thing a little bit by hand, and I'll show you how to do it in Desmos also. All right. So let's just make a little chart here just for kicks. All right. Let's say we have a -3. All right. So x is -3. Which part of this function do I concentrate on? The top one or the bottom one? Why?
It's less than 0. Less than 0.
The condition says if it's less than 0, you use this, right? So if I have a -3 there, then I'll just take -3, put it in there. So -2 times -3. I'm really writing this stuff out. I wouldn't expect you to, but 7. So -3 and 7, someplace way up there. Okay. What if it's a -1? Which one do I look at? Same. What about 0? X squared. So this function, this -2x plus 1, comes down to here, okay, almost to 1, and then it's open right there, right? Because as soon as x hits 0, it jumps down here. All right, so that's kind of an open dot right there. All right? Okay. Then what happens at 1? Continues with the x squared. So we'll get something like this. All right? Not very good. I'm not doing a very good job of drawing this, but all right. That is a piecewise function. Okay? All right. Now, they don't have to be connected. Okay? The one I drew up there is connected. They don't have to be. These two aren't connected. This is open and closed. So they're not connected. It has to have an open and a closed overlap, or else it's not a function, so that doesn't work. All right? And you can have as many pieces as you want. You could have 10 pieces of that if you wanted to. All right? Don't worry, you won't have any. Okay? I wouldn't give you more than 10 pieces. All right. let's try doing, so how would we graph this in Desmos? Let's take a look. We'll go here. All right, I'll show you how to do it. You can put y equals or f of x equals. I don't necessarily like this part, how Desmos treats this, but I'll show you. So, okay, here's how it works. First, you got to get this, hit the ABC button, and you're going to go to the curly Q brackets right here. Okay, hit the curly Q brackets. Now, it's just the opposite of the way it is in mathematics, which is why I don't like it. You have to put the condition in first, and then you put in the piece. All right, so here you're going to say, we'll put in the same one I just did. So I'm going to go x less than 0. All right, x less than 0. Then, and this is where it gets a little tricky on your phone if you're using your phone. You have to go to the ABC. All right, you can use a keyboard too, but if you're using your phone, I want to show you. You have to hit the up, the little up for capital letters. Right here is a colon. All right, in mathematics, a colon stands for such that. So what we're saying is, what we're going to put next is the function. All right, so then I'm going to go, what do I have? Negative 2x plus 1. Okay, there's the first piece. You can see it drew it already. Now, I'm going to put a comma. Okay, and now I put in the second condition, which was x greater than or equal to 0, back to the colon. Remember, you got to hit this shift, and then we put in x squared. All right, and there it is. Okay, that's how you do it. So it's condition, colon, function, comma, condition, colon, function, inside curly Qs. And that is a piecewise function. Okay? Did everybody get it? We're good? How to do that? Okay. That is a piecewise function. All right. That's pretty much all there is to section 1.4. Is there any more questions on, so we did the power function stuff, okay? Looked at the ceiling, floor, talked about the domain and ranges, discontinuous, piecewise, and that stuff. That's kind of what we talked about. Any questions on anything?